In this video we are going to discuss example 6.6.2. So here a system has been given and we could verify that this system is a reversible system. Okay, so now it's been asked to show that this system has a homoclinic orbit in the half plane, which is where x is positive. Okay, so in this region there exists a homoclinic orbit. That's what we need to show, and we need to show that only using reversible arguments. Okay, so let's see how to do that. So the fixed point, so the fixed point is the origin. Okay, so we know that y is equal to 0 gives x dot to 0 and x is equal to 0 give y dot to 0. So that's the fixed point. Okay, and in that fixed point, if we do the linearization method by calculating the Jacobian, we could identify that it's a saddle point. Okay, so which means we will have two eigenvalues. One is a positive value and another one is a negative value. Okay, so if I calculate the eigenvector for the eigenvalue which is negative, I will get a direction of the stable manifold. Okay, and if I do the same for positive eigenvalue, I will get the direction of the unstable manifold. Okay, so now let's choose the unstable manifold, and if we do the analysis, we will get 1, 1 as the eigenvector. Okay, so now all I know is origin is a fixed point, and that fixed point, a trajectory will come out of that fixed point, which will be in this direction, 1, 1. Okay, so how does that look in the phase portrait? So the phase portrait in the x-axis and y-axis, let's forget about this entire curve. So at this moment we know that this is the fixed point, a saddle point, and from this point a trajectory will come out in this direction. Okay, so far I know, but after that what will happen to that trajectory is not known. Okay, at this moment it's not known. Okay, let's see. From this equation, what we could say is when y is positive, okay, then x will keep on increasing. Okay, so it comes out of this direction, so it's in the positive y direction, right? So it's in the positive y region, so x is going to keep on increasing. Okay, it's going to keep on increasing, so it's going to go in this direction. It's not going to reverse like this. Okay, fine. Now let's look at this equation. Here when x is very near to the origin, okay, at that time this will dominate compared to this. Okay, so then y dot will be positive. Y dot will be positive, which means y will increase. So x, so near to the origin, x will also increase, y will also increase. Okay, however, when x becomes a very large, not very large number, x becomes a number larger than or equal to 1, let's say. Okay, when it's equal to 1, then y dot is 0. Okay, so at that point there will be only change in x and there won't be any change in y. okay, but the x has got increased more than 1, right? So because there is a change in x, and because of that now this term will start dominating compared to this term. And what will this term will do? This will decrease the y value, okay, this will start decreasing the y value, and because of that reason the y value will start reducing, but still it's in the positive y region, the x will keep on increasing. So therefore we are observing the increase in x but decrease in y, okay. So if this is going to continue, okay, if this is going to continue, then at some point the trajectory will end up at the x-axis, the point where the x get vanished, sorry, the y get vanished, okay. So that's 1/2, okay. So that's a trajectory which starts at a point in the x-axis and end at the point in the x-axis. So now we have this one, and now if I use this reversibility property, then I could say that it will continue to have the trajectory which is going to be a mirror symmetry of this one, okay, and therefore we will get a trajectory which is this one, and that is a homoclinic because it starts at this point and then ended at the same point, because we can't say that this is a closed orbit because it's a saddle point, right? So it starts at this point and ends at the same point, okay. So yeah, so we have showed that using the reversibility argument that it has a homoclinic orbit, okay. Now we'll see one more example, which is this one. So in this one what we have to show is, we have to show that this system is reversible, okay, but not conservative, okay. So well, first, is it reversible? If we do the transformation for t and the transformation for y, we will not observe that we are regaining this form, but if we do this additional transformation, okay, then we will get this form back, okay. I'll leave that as an exercise for you, okay. And if you do that, we will get back this form, and therefore it is a reversible system, okay. So while you are saying that it's a reversible system, you have to say under what transformation, okay, fine. So so now we know that this is a reversible system under these transformations. Is it a conservative? So we have to show that this is not, okay. We are going to show that by claiming that a system is going to have a fixed point which is going to be an attractor or a stable node, okay, because a conservative system cannot have a stable node, right? So let's identify the fixed point and let's see whether we have any stable fixed points, okay. If it is, then it is not a conservative system, okay. Now let's try to identify the a fixed point, and by equating x dot equal to 0 and y dot equal to 0, we will have 4 fixed points which are plus or minus pi by 2 and plus or minus pi by 2, okay. So 4 fixed points. Now among these 4 fixed points, if we use linearization technique and if we solve, we can identify that one of the fixed point is stable and another fixed point is unstable, and 2 fixed points are saddle points. Okay, so from this we could say that it is since we have a stable node, so we can say that it is not a conservative system. Okay, so now let's draw the phase portrait. Okay, so if let's say so this is the computer generated one, and let's say even by using numerical method or some other method, if I could plot this half, okay, when y is positive, so say I have constructed, okay, can I construct the remaining thing? The answer is yes, and we can construct the remaining thing, but in order to construct the remaining thing, we cannot just mirror along the x-axis. Okay, we have to mirror first with respect to x-axis and then with respect to y-axis, but it doesn't matter. That operation is the operation can commute. Okay, so therefore first you have to mirror with respect to x and with respect to y. Okay, and if you do that, you will get the complete picture. And also in order to choose the arrow mark, you have to use the other transformation, which is t is equal to minus t. T is transformed to minus t. Okay, and one more thing, instead of making a transformation or a mirror transformation with respect to x and with respect to y, what you could do is equivalently you could do a 180-degree rotation. Okay, so that's very same as having two mirror projection. Okay, so if you do the rotation, then this point will come to this point and this point will come to this point. Okay, and because of the time reversal, if you see here we observe that the trajectory is coming out of this fixed point, where here we could observe that it's coming towards the fixed point. Okay, so right, so that's the phase portrait, and by knowing the half of the phase portrait, we could capture the remaining half. Okay, so that's about that example, and in the following video we'll see some physical applications. Okay, thank you.